Welcome. Still on one-dimensional kinematics, and we had talked about 2 videos ago equations for constant acceleration motion. And then in the last video we talked about problem-solving techniques on how to solve these types of problems. But what type of problems are constant acceleration problems? Well, actually it turns out there's a big class of objects called falling objects. When an object falls, like this marker falls down, it is actually being accelerated to the center of the Earth. This acceleration, of course, it stops when it hits the floor, but this acceleration actually has a number associated with it. On the surface of the Earth, the gravitational acceleration downward is approximately 9.80 meters per second, or meters per second squared. Now, that's the acceleration. Sometimes it's a sub g. The acceleration of gravity is equal to, it's downward, because our coordinate system down is negative, g. But what is g? This lowercase g is represented in your textbook as a number, 9.8 meters per second squared. This is true for all objects. A bowling ball or a feather will be accelerated downward at 9.8 meters per second squared. So when I say downward, that means negative. It's true if we ignore air resistance. Of course, if you do drop a feather, you clearly know it gently floats down compared to a bowling ball dropping. However, in physics, again, one of our initial assumptions, we're going to pretend that there is no air resistance. This experiment was actually done on one of the lunar missions. An astronaut actually had a hammer in one hand and a feather in the other, a falcon feather, dropped them both, and they both hit the moon at the same time. Now, the moon has a slightly different acceleration magnitude than the Earth does, because the moon is smaller. But that proved that objects fall at the same rate. Now, Galileo famously, probably allegedly, walked up to the Leaning Tower of Pisa and dropped 2 stones of differing weights off the edge, differing masses off the edge, and was astounded that they fell at the same rate. Because for 2 stones, 2 objects, imagine 2 bowling balls, a 10-pound bowling ball, and if you could imagine a 20-pound bowling ball. Since they're around the same size, they'll have about the same air resistance. Not exactly, but about. So you can do this experiment. So, this is on the surface of the Earth. Now the Earth is round, right? It's a sphere or an oblate spheroid. So this changes slightly depending on where you are on the Earth. On the top of Mount Everest, it's a little bit smaller. And the Death Valley, California, it's a little bit bigger. It varies from about 7877 to 9.82, 9.83 approximately. So this number is an average over the surface of the Earth. So it's downward, which is why it's negative, because we define down to be negative y. It has a magnitude of 9.8 meters per second squared. What does that magnitude mean? That means that every second, the velocity changes by 9.8 meters per second, right? It's 9.8 meters per second every second. So after 1 second, the velocity of the object would be 9.8 meters per second. After 2, it would be 19.6 meters per second, right? Double this. After 3 and so on, it would be, if this is approximately negative 10, after 2 seconds, it'd have a velocity of negative 20 meters per second, 3 seconds would be negative 30 meters per second, and so on, approximately. So falling objects, if we ignore air resistance, are constant acceleration problems. And we'll be doing a lot of example problems, and your book does a lot of example problems of these free fall problems. Now, we're going to worry about one dimension right now, so objects that fall directly down. But of course, another way of free falling is objects that have some x component of motion as well. That's 2-dimensional kinematics, and we'll be worrying about that in following chapters. Because free fall constant acceleration equations are so common, we'll be solving for objects that fall, right? Or objects that are fired, a baseball being thrown or hit, a tennis ball being hit, a cannonball flying through the air later on when we talk about 2-dimensional kinematics. free fall constant acceleration equations are actually slightly different than the ones we had before. They're identical to the ones we had before, but we're dealing with vertical motion, so the initial x position becomes the initial y position. Right? The final x position becomes the final y position. So any x displacement is really any y displacement. And then finally, and most importantly, the acceleration is equal to negative g. Right? This is free fall. So the acceleration is downward with a magnitude of 9.80 meters per second squared. So acceleration is equal to negative g. Now going back to those equations we had before, those 5 equations, we can modify 3 of them easy enough. You can do the other 2 on your own fairly simply. Here, the velocity, this is y direction velocity now, because we're talking about one-dimensional y motion. The final y velocity is equal to the initial y velocity minus g times t. Remembering that g is equal to 9.80 meters per second squared. So wherever you see this g, you substitute in 9.80 meters per second squared. So if you recall the other equation, there was a plus a here instead of a minus g. Well, the acceleration is minus g, so substituting in minus g for where a is turns this into a negative sign, and the a becomes a g. Just an algebraic substitution, very straightforward. Same thing with this equation here. Y position is equal to the initial y position plus the initial y velocity times time minus 1/2 gt squared. This used to be plus 1/2 at squared, but when you substitute in, the acceleration is equal to minus g. That negative sign comes up front, and the a turns into a g. And then finally, again, the last equation, the final y velocity is equal to the initial y velocity minus 2 times g y minus y naught, the quantity y minus y naught. Now g, remember, is positive 9.8 meters per second squared. So g is the magnitude of the acceleration due to free fall. That's the magnitude. The direction is given by the negative sign, which is why these symbols turned into negatives rather than positive. So some books don't give you these equations. They just give you the same set of equations with a and then tell you, well, a is minus g. So when you plug in the acceleration, make sure you remember it's negative 9.8 meters per second squared. Other books like yours will do this substitution, show g, remember that g is positive 9.80 meters per second squared. The direction, the negative sign, is explicitly given in the equation already.